So does anyone need a pencil, scientific calculator, or a pencil? Both? One? Okay. You have pencils here, you might need it. And calculator, yes. I also need one up here. Need a calculator? Okay. Now, so folks, using a calculator consistently throughout, throughout your math course is probably the best bet. And you're going to come to see why, especially today, because different calculators will work a little bit differently. I mean, they'll do the same thing, but the way you would input something into the calculator might differ based on the type of calculator you have. Remember in grade 9 we talked about calculators that can hold the display and some that cannot hold the display? Things like that will certainly matter today. That's why in grade 9 we tell you, we're like, hey, get a good one that'll last you to grade 12, and that'll be the end of it. Okay, recall here. So we kind of just did a little bit of this. Here's our triangle, right triangle, and we're using angle A as a reference. They want us to, label the triangle and also identify the primary trigonometric ratio. So if this is our reference angle A, of course this side right here must be the hypotenuse because it's across from the 90. And a lot of us go right to the adjacent, yeah? They say, okay, well this down here has to be the adjacent because we know that the reference angle touches the hypotenuse and the adjacent. And lastly, over here is the opposite side. Labeling the triangle is always step one. It's always step one. So sine of an angle, sine of A equals opposite over hypotenuse, and that's where SOH comes from. That's so in SOHCAHTOA. Cos of angle A is CAH, adjacent over hypotenuse, and tan, of course, is opposite over adjacent. Now remember, just like from the other day, the way you label your triangle is always from the perspective angle or this reference angle down here, this angle A. If we chose a different angle, perhaps the one up here, for example, whatever angle that might be, the way we label our triangle would change, yeah? Because now, if we use this side here, this would be the opposite. This would be the adjacent. So things do change based on that reference angle. So it's important that, if you choose a reference angle, you kind of use it throughout whatever you got to do in the question. Unless you wanted to change it, of course, which is totally fine. You just got to be a little bit careful. Yeah. Great question. Could the reference angle ever be 90 degrees? The answer is no. It can't. Example 1. Okay. This is where we're going to be using our calculator and kind of getting used to the functions. So it says your calculator must be in this particular mode. It's called degree mode. So if you look at the display of your calculator when it's turned on, so for my calculator, I see a 0 there, and then at the top it says DEG. Yeah, this is the one we want. That's what we want. Some might say grad, or some might say rad, and these are the ones we do not want. So take a moment and look at your calculator, and if it's in anything other than DEG, please let me know, and we'll help you get it to DEG. Yeah? Or, yeah, see your calculator, it's just got a big capital D at the top there. Do you see that, capital D? Yeah, there's a capital D. See, there's a capital D, capital R, capital D. That's good. Did you have that capital D there? Yeah, absolutely. I didn't see the lesson, but yeah, absolutely. Yeah, here says rad, and there's a button right here. It'll switch to rad, and then it'll switch to day. So that's what you want. You want degree. It's called degree mode. Or I think it's either a DEG or a capital D. All good? Yeah, nice. If you see that capital D, you're in good shape. That's perfect. How about you? Yeah, capital D, that's perfect. Yeah. Capital D, you're good. See the top thing? Yeah, but see up here, on the display, DEG, that's perfect. That one will it's a DEG right there. That's perfect. That's what we want. Calculator questions, anyone? All good? Okay. If your calculator is in a different setting other than DEG, your answers will be off. They will be, like, the work will be right, but the answer would be off. So just to give you a heads up, so when you're dealing with trigonometry, you want to make sure the calculator is in DEG mode. Now, the way we input things into our calculator might differ depending on what calculator you're using. So I know, for example, Will's calculator is one that does not hold the display. So if he wanted to take the tan of 25 degrees, he would have to type it in a little bit differently than someone who has a calculator that can hold the display. So what I type in is I type in first tan, then 25, and I press equals. Now sometimes if you just hit that tan button, your calculator might open up a bracket like that. It's like, oh yeah, tan of what? That your calculator's waiting. He's like, yeah, what do you want? And then if you type in 25, don't forget to close that bracket, because I know if you're using the calculator I suggested, it might already have that bracket open for you, right? And if it does, be very cautious. You want to close that bracket. Having that bracket open is really useful, I promise, at some point in your math life. But for right now, just doing small little calculations here, you want to close that bracket and get into that habit of closing the bracket. So if your calculator does not hold the display, like Will, for example, you're going to have to type it in backwards. Instead of, if it holds the display, 10, then 25, then equals, great. If it doesn't hold the display, you're going to have to type in 25, then press 10, and then it'll give you the proper decimal. Okay, so we should give that a shot. And like I said down here, if your calculator puts the angle in brackets, you must close the bracket, and that's for a lot of us probably in this class. So you get 1025. If your calculator's in degree mode, what do you get as a decimal? And we should round to 4 decimal places. So what'd you get? 0.4663, and then the next term is a 0, right? There's a 0 there, but that 0 will not round the 3 up, so we'll just leave it as 0.4663. Great. How about sine 30? So in your calculator, you type in sine, and it opens up. Type in 30, close the bracket, hit equals. And what did we get as a decimal? What did you get? For this one in particular? Yeah. Because sine of 30 is exactly just 1 decimal. It is exactly 1/2. Yeah, 0.5? Now, I mean, if there's sometimes the textbook might say round to 4 decimal places, and you might just do something like that, which is a little weird, and I would not expect you to do something like that. 0.5 is great. Sine of 30, yeah, 0.5. Next, cos of 75. What do you get? Yeah, what do you got, Tessa? 0.2588, and then that next term is a 1, so that 1 will not round. It will not round that 8. Okay, that's half the battle. anyone have any questions about typing in things like that in your calculator? Because that will be a common thing that we do. So far, so good? Okay. Let's go a little bit more here. How about finding an angle? Again, your calculator must be in degree mode. You got to have that big capital D, or it says DEG on the display area. And if it's not there, there's a reset option on your calculator. Okay, we know. So, folks, if we want to calculate, if we look at this example over here, A, it says tan of theta equals 0.3711. Okay. Now, remember, even this year, even in grade 9, it's like, oh, we want to solve for theta, right? That's what we want to do here. We want to solve for theta. Probably thinking to yourself, okay, well, that means we have to get rid of that 10 there, right? Now, what's really going on between tan and theta is not just multiplication. It's not like you just divide this side by 10, divide that side by 10. There's a lot more than just multiplication going on between that tan and that theta. If we want to undo tan, just like you know how we undo addition by subtracting, we undo multiplication by dividing, right? If we wanted to undo tan, what we would do is the tan inverse. So it looks something like this. We have tan theta equals 0.3711. And what happens is, if we want to get rid of that 10, on one side of the equation, we're going to do the tan inverse of this side, which is a little strange. And then we do the tan inverse of the other side, like that. And what happens is that the tan inverse cancels with the tan, which is great, because now on that left side, all we have is theta. And on the right side, we have the tan inverse of 0.3711. So in your calculator, this is what we're going to have to type in. The tan inverse of 0.3711. Now, the way we get the tan inverse is by pressing the button that's usually located in the top left. It's either a shift button or a second function button, and you press that second function button once, and then you press tan. And what should come up on the screen is a tan inverse. When I say inverse, it's got that exponent -1 there. That's telling us that it's tan inverse. It's not 10, it's the opposite of 10, it's tan inverse. Does everyone have that button? So tan inverse, then it might show a bracket for you, and you just type in 0.3711, close the bracket, you press equals, and what do you get? 20.35, 20.36, 20.4 even. Let's do one decimal place, 20.4 degrees. Did anyone else get 20.3599? Yeah. Usually final answers are always rounded to one decimal place. In fact, the textbook might even say round to the nearest degree, but I always like one decimal place. I do. Now, do we have to Will, question? Can I have a look at what you typed in? You have to put in 0. Oh, it's not 0.37, it's just 0.37. Yeah, and then second function, 10. There you go. Okay. Okay, great. Question might be, do we have to show all of this work? Well, compare this to grade 9. You know how we balanced the equation a whole lot in grade 9 and take away this side, take away that, and eventually you got into the habit of just moving it across the equal sign and it changes its operation. Do you remember that? That's what we're going to kind of get into in these examples. I mean, showing you why this exists is great. Now that we've seen this on part A, we can appreciate it and understand what's going on. Let's do the next one here. Like sine theta equals 0.390. 0.907. Well, if we wanted to solve for theta, that means that we're kind of like bringing the sign over, and it changes into the sine inverse of the decimal, 0.3907. And again, to get the sine inverse is very similar to how we got the tan inverse, and that's by hitting that shift or second function key, and then sine. So sine inverse, open the bracket, 0.3907, close the bracket, and what did you get? Yeah, 22.998, so we'll just say maybe 22.99. We'll round that to 23 degrees. Because this 9 rounds that 9 to a 10, which comes over to the next fifth. Lastly, this is much more our style. Oh, look,
I put like the decimal and multiply by
no, it's the sign this time. If you hit second function 10, yeah, it's going to give you a different answer. So you have to make sure that when it's sine, we got to do sine inverse. Right? Because the opposite of sine is the sine inverse. The opposite of sine is not the tan inverse. Right? Now this one here, this is probably what we're going to be up against, right? And this kind of looks familiar. Cos is adjacent over hypotenuse, right? And this is kind of where we're headed. So again, if we wanted to solve for theta, we're going to have to take the cos inverse of this fraction, 9.1 over 17.4. So cos inverse of the fraction. What do you get? Anyone? 58.46. So we'll round that to one decimal place and say 58.5 degrees. Don't forget the little degree symbol. Because we are talking about angles, right? Theta is an angle. Okay. Any questions for me about calculator use or any of this stuff? Any questions? Yeah. Well, there's two ways. Two ways to put the fraction into the calculator. Put in the fraction button, but what I like to do is I can type in 9.1 divided by 17.4. The calculator knows that bracket first. It'll give me the crazy decimal in there, and it'll also then do the cos inverse of that. Yeah? Well? Now, for you, the calculator is a little bit like you got to type it in a little different. So we got to do 9.1 divided by 17.4. Then do the second function of COS. Yeah? Yeah. So it's shift. So see shift button here? So you press that, and then it's close. So now instead of just close, it's close into close. Yeah, yeah. But if you press shift, then close, it'll be close. And that's 9.1 divided by 17.4. Close the bracket. There you have it. You're welcome. Yeah. Good? Okay. Yeah, folks, it does take a little bit of practice with the calculator to get used to these types of things because this is very unusual. This is probably the first time we're ever using the calculator in this sort of way. So if you do have questions, please let me know because it's important that we know how to use this tool. Because the math, I know you're going to fly by, but sometimes typing in the calculator might just be the issue. So please let me know if you have calculator issues. Okay, so let's do some math. Yeah, let's do some math. Let's use these. Let's use actually everything that we already know up to this point, and we're going to be able to solve for angles. It says here, determine the value of theta to one decimal place, and we know Theta, the variable, it's referring to angles. So we're going to have to solve for this angle right here. There's theta. Because we're solving for it, it becomes our reference angle. So from this angle, we're going to first label the triangle. So that means right across from the 90 here is the hypotenuse. This must be the adjacent. And down here must be the opposite. And after yesterday's work, you're like, yeah, I know. But folks, now that we are experts at setting up the trigonometric ratios, you might notice a little bit of a problem here. We don't have all three of the side lengths, like we did yesterday. So when we're thinking of SOHCAHTOA, and maybe I'm going to write that up here, only one of these three primary trigonometric ratios is going to work to solve this problem. So this is where we kind of got to think about what we have and what we don't have. Yeah? So what are the two side lengths that we have? And if you look at this diagram, it's very clear that we have the hypotenuse. It's 13. It's given to us. We also have the opposite side. It's right there. It's 5 centimeters. So which one of the three primary trig ratios involves the hypotenuse and the opposite? Ken? Yeah, sine. This first one here. So some people might look at it like that, like, oh, I have an O and I have an H. Which, there's only one that always works. There's only one. And look, A and H, no. O and A, no. That will not work. There's only one that'll work every single time, and in this case, it's sine. So what we're going to do is set this up. Sine theta equals opposite over hypotenuse. And remember, it has to be in that order, opposite hypotenuse. So we can say something like sine theta equals 5 over 13. And we're good at that. We know the opposite side is 5. We know the hypotenuse is 13. But now we have to solve for theta. Does this look a little bit familiar? A little bit? If we want to isolate and solve for theta, that means the sine has to come over to the other side, right? So it's not like we just divide by sine. To get rid of sine, we have to do the sine inverse . So we do the sine inverse. Really, we did it on both sides. And on the left side, it canceled out. And we're left with the sine inverse of 5 over 13. So we go to our calculator. Second function, sine, bracket, 5 divided by 13, close the bracket, press equals, and we get theta equals 22.61, so 22.6 degrees. Feel all right with that? So we now know that that angle is 22.6 degrees. Great. And if we have that angle, then we can certainly solve for the third one if we ever had to, right? Because all triangles must add up to 180. So it's just the last angle to solve for. Okay. Part B. Similar idea. We're solving for theta. So here is our reference angle. It's theta. It's given to us. It's right there. And we have, first thing we have to do is label the triangle. So this is for sure the hypotenuse. This is the adjacent. And this is the opposite. Now some of you might say, well, okay, there's two ways to look at this. Just like there was two ways to label the triangle, right? It depends on how your mind kind of looks at it. Some people might say, oh, look, I don't have the opposite side. I don't have it. So which trig ratio does not involve the opposite side? Which one does not have an opposite in it? CAH. That one does not have an opposite. Or you can look at it and say, okay, which one has hypotenuse and adjacent? That's the way I like it. I'm like, oh yeah, which one is A and H? Which one is that? And it's cos. So we're going to use the cos ratio here. That's how we know to use the cos ratio. Cos equals adjacent over hypotenuse. And now we're going to fill in everything that we can. We don't know theta, so it'll remain theta. The adjacent side is 5. The hypotenuse is 11. Now, if we want to solve for theta, we're going to move the cos over, and it becomes cos inverse. Cos inverse of 5 over 11. 5 divided by 11. And I got 62.96, which is really would round to 63 degrees if we're rounding to one decimal. 63.0. Okay. Any questions so far? Can I get a check-in? Like, yeah. I see what some of the side like, okay, this is pretty good. Yeah, I think I know what's going on. Come down like, whoa. Yeah? Okay. So that tells me I can kind of just go, okay, here's the reference angle. Yes. Of course, I always label the hypotenuse first. I think it's the best. Opposite, the way my brain works, and then adjacent. Before I even move on to the next steps here, I confirm it. I'm like, yeah, okay. Okay. Yes, good. Which trig ratio involves the adjacent and the opposite? Which one has A and O? A and O. There's only one. And so we're going to say tan theta equals opposite over adjacent. Lovely. And we're going to fill in what we know about this. Tan, we don't know theta. The opposite is 6.8. The adjacent is 4.5. And here we go. Theta equals, and this is where we bring the tan over, and it becomes the tan inverse of 6.8 over 4.5. Tan inverse of 6.8 over 4.5. And notice how it is an improper fraction. That's totally fine. I got 56.50. Okay, theta equals 56.5 degrees. Folks, just to note, whenever, the only time you will ever use, maybe we could even write this down underneath here. The only time you use the inverse is when you're solving for an angle. Oops. Inverse. We only use the inverse. That looks like it says metaverse. Hold on. Let's not go there. When solving for angles. That's the only time we use the inverse. It's only used for angles. When we solve for sides, we don't use the inverse. This is specifically for angles. And it kind of makes sense because we're solving for theta. We need to get rid of tan. So we'd have to do the tan inverse to do that. Questions about solving for angles before we go on? Now's a perfect time. Feel good with it? Great, I knew you would. Okay, example 4. Now, we're solving for side lengths here. Find the length of x to one decimal place. And maybe a lot of us are thinking, oh, it's a right triangle. It's Pythagorean theorem, right? That's kind of where my head goes when I see right triangles coming out of grade 9 for sure. But notice, we only have one side, not two of them. So the Pythagorean theorem won't really help us out a whole lot. I always write this at the top of the page, and I highly suggest you do too. It's just always nice to have. So we have example A. Notice we have 37 degrees down there. It's given to us 18, and then x. We need to solve for x. So very similar, very similar. We're going to use this as the reference angle. Will brought up a great point. We can never, ever, ever use the 90 as a reference angle. It gets a little sticky. We can talk about that near the end. If you want to bring it up again, I can show you why that's a little bit weird to use the 90, okay? But for now, just take my word for it. But I'll show you why. So we're using 37 degrees as the reference angle, and again, we're going to go ahead and label the triangle as we always do. Here's the hypotenuse, this is the opposite, and this is the adjacent. Okay. So, now it's like, well, which trig ratio do we use here? Well, we got to kind of think about this a little bit. We need to solve for x, so we have to take it with us. Undoubtedly, it has to come into the equation with us because we're solving for it, for sure. What else do we know? Oh, I guess we know the hypotenuse is 18. Those are the only two side lengths we really need. That's it. We have the angle, which is great. So which trig ratio is O and H? Hypotenuse and opposite. Which one? It's sine. It's this first one here. So we'll say, we'll first write it out. Sine theta equals opposite over hypotenuse. Now, once we have that there, and it's a really great step. Please don't lose that step. It's so good. We need to now fill in the blanks, basically. This is weird, because now we know what theta is. We know the angle. It's 37. So we're going to say, okay, sine of 37 equals opposite, which is x, over hypotenuse, which is 18. And I think I got to move this over just a little bit. There we go. Now what we have to do is solve for x. Think about similar triangles. Think about it just for a moment. How did we solve for x in similar triangles when it was like this? Do you remember? How do we multiply each side by the denominator? So it's exactly what we do here. Oops. We're going to multiply this side by 18. Okay. And whatever we do to one side of the equation, we must do the same thing to the other. And what happens is divide by 18 cancels with times by 18. So what we have is 18 times sine 37 is equal to x. So in your calculator, you can type it in just like that, but on your calculator, you'd have to do it kind of backwards. Do sine 37, get the weird decimal, times it by 18, and that'll be your answer. $10.83. Can I get some nods? Yeah? Okay, great. So we'll say 10.8 equals x. And we can go back to the diagram and say, okay, this is 10.8 centimeters. Question? Let's have a look. Can I see how you're typing it in?
Yep. Oh, see, it won't be second because that's only for angle. It's just 37 and sine. Yeah, and then times 18. Beautiful.
Okay, I got to kind of squish this a little bit, give myself a little bit of room here. Does that work? Is that okay? Is that still readable in the back? Okay, thank you. Okay, next one. Same sort of idea, and I know, after that one example, you're probably just burning through the rest of them. But I promise you, stay with me because in this last one here, it gets a little bit weird. Here's our reference angle, and I know that because it's the acute angle. It's the only one that's there. I mean, sure, we could solve for this acute angle and use that one if we really wanted to, but that just seems like it's too much work, kind of irrelevant work. This is the hypotenuse, opposite, and adjacent. Okay. So we're solving for x. It needs to come with us. We're grabbing the opposite. And what else are we get? Well, we don't have the hypotenuse. That would not help us at all if we took the hypotenuse. There's nothing there. But we have the adjacent, so we can use that as well. So which trig ratio involves the A and the O? There's only one. and it's TOA. So we'll say tan theta equals opposite over adjacent. In our next line, we begin to fill in these blanks. Tan theta equals opposite, which is x, over adjacent, which is 30. And you know what to do. We're going to get rid of the divide by 30, because we want to solve for x. We want x. So we're going to have to multiply each side by the denominator. Oh, sorry, whoa, hold on here. I forgot something, didn't I? Not tan theta, tan 51. Getting too excited. So we multiply each side by 30, and divide by 30 cancels with multiply by 30. So we should be left with 30 times tan 51. Rate in the calculator, Will? 37, I agree. 37 equals x. 37.04, so 37.0 is great. Now remember, this is centimeters, so we'll say, okay, this side is 37 centimeters. And it's kind of nice now, because once we have two sides of the right angle triangle, if we wanted to solve for the third one, we don't necessarily have to use trigonometry, because we could just use the Pythagorean theorem, which is a lot less steps, right? If we wanted. And this last one here is a little bit strange, but we follow the exact same steps. Regardless if it's solving for angles or sides, the first couple of steps are the same, but the way in which we solve would be a little bit different. Here's our reference angle. This is opposite, hypotenuse, and adjacent. Which two side lengths are we stealing from here? Which two? Opposite and hypotenuse, perfect. And which trig ratio is that? Sine theta equals opposite over hypotenuse. Let's fill in the blanks here. Sine of 42 equals opposite, which is 4.5 over x. Now, why is this one a little bit different than the rest of them? Yeah. Yeah, x is now the denominator. Like, that's weird. So this method here of just multiplying by the, and this method here, they kind of just go out the window a little bit, don't they? But if you think back, we have run into this situation before, haven't we? We've run into this situation in similar triangles. We had x at the bottom. Now, what did we do in similar triangles? What did we do, Ravina? We flipped it. Yeah, oh, sorry. We did flip it. So on the right-hand side, we are going to flip this fraction. So it's going to become x over 4.5 because that's what we want. Now, what happens to the sine 42? It sounds a little bit strange. But remember, anything is over 1, right? Everything. Just pretend there's an over 1 here, just for a second. Now, let's flip the other side. We will have 1 over sine 42. Now, we're cooking with fire. We're going to multiply this side by 4.5. That felt good. And we're going to multiply this side by 4.5. That felt a little weird because it's now we're multiplying 1 over. But it's fine. Because our calculator is really going to help us out here. 4.5 bracket. 1 divided by sine 42, close the bracket. What did you guys get? What do you got? 2.5? Yeah, 6.7. I like that. 6.7. So we can go to our diagram and say, this is meters, So we'll say 6.7 meters. Great. Okay. Good. Folks, I have here, sorry, before I even go on, is there any questions, Will? You're going to have to do it? Oh. Okay. This would be a little bit weird, wouldn't it? With that calculator. We'll talk in a minute, okay? I'm going to come over there and show you. Look, there's just two questions of solving for a side length. Yeah? Try it on your own. Two questions for solving for an angle. Try it on your own. And if you wanted to make any notes to your future forgetful self, like anything that came up, you're like, oh, that was actually, yeah, maybe I could use that. Then that's the spot to write it, okay? So start off with this, and Will's gonna come on over there.
We are going to do this. So let's say 4.9 times 1 over 0.6691. We're going to take the first whole. And then times it by 4. Well, I would just write it down. So I take that extra step, write it down. Yeah, go ahead. Yeah. Mm-hmm. Oh, the 10 is the one that's big giant decimal over the internet. Yeah. 10.6. Yeah. I know these trigonometry are actually like way inside that. And like, if you ask me, oh, so what's the stop again? It doesn't know all the time. It doesn't know what time it is. 311 is there. Oh. So yeah, the sign of 9. And then you get 1. Then you sign of 180. You get 2. You sign of 7. You get negative 1. Goes and goes and goes.
Okay. I'm gonna start taking these up. Yeah. This one, and this one. Yes? Sure.
Yeah. Yeah. Always. I do the same thing like bracket. One bracket. Yeah.
Folks, another great point was brought up here. When you're typing this into your calculator, like this part of it right here, a lot of people might go 120 bracket 1 divided by, and then when you hit cos, so you're typing this in 120 divided by bracket 120 times, sorry, getting ahead of myself here. 1 divided by, and then when you press that cos button, it's ready for you. It's got that bracket open. It's like, cos of what? Yeah, what do you want? And you type in 32. Then if you close the bracket, you might think you're in good shape, but you also, remember, like, we have to close this bracket too. So just be cautious of that. That's a very good point. Notice how I closed the bracket of the cos 32, then I gotta close the bracket of the whole thing that we're working on here. And that would be in this step right there. Yeah? Okay. And we should get 141.5 meters. Opposite, hypotenuse, adjacent. We need O and H, that's sine, lovely. Sine theta equals opposite over hypotenuse. Sine of 63 equals x over 15. And we love this one. Multiply each side by 15. The 15s cancel, and we get 15 times sine of 63, 13.4.
Yeah. So it's like we gotta grab this one for sure, and then well, because we don't have the option.
Folks, any questions about solving for sides on your own? Everyone confirm their answer. The first one, 141.5. The second one, 13.4. Good, good, good. Okay. Yes? 0.2? 142? No. We want one decimal place. Okay. So when we're solving for the angles here, this is again kind of going back in time a little bit. Folks, think of trigonometry like this as right angle trig. There's always 3 unknowns. There's 2 side lengths and 1 angle. So you always got to grab what, like, we know we're solving for the angle, so we need the 2 side lengths, right? So we need this one, and we need that one. A and H, that's cos. A 13 over, sorry, Oh, look at me. Silly. Didn't even follow my own rules. I got height adjacent. Theta equals the cos inverse of that. .6 degrees. Yeah. And lastly here, opposite hypotenuse adjacent. O and A, that's 10. Yes. Sure.
Question.
Okay, folks, there's some homework here from the textbook. It's at the bottom. Try these. You're going to fly through. What's that?
Yeah, just type it in. Which side? Yeah.